what Seth is doing is solving for the components of each direction. So this has an x component in the x direction, and it will have a y component, so vy and vx. When you're using x direction numbers, you can only use the components that are pointing in that direction. So we can only use vx, we can only use 20. Numbers like 5, numbers like 10 meters, numbers like vy, we can only use in our x equations, or our y equations, right? So we want to find the components of these first. Then, after we find the components, throw that number away and never use it again. So what are the components? What is vx? How do I solve for vx? I've got a triangle, 60 degrees, and one side is 25. So how do I solve for the x side?
The cosine of 60.
Cosine of 60 is equal to
25 over x.
x over 25. So 25 times the cosine of 60 will give me my x velocity. So half of 25 is 12.5. Okay, see that? You have to do that first. If you attempt to use 25 meters per second at all in the problem, you're going to get a component. You have to find the component in the x direction first. Well, what's the final velocity in the x direction?
Same thing.
Same thing. And why is that?
I don't remember.
What's the acceleration in the x direction?
0.
0. So why is the final velocity the same? There's no gaining speed, there's no losing speed, there's no acceleration, so that cannot change. Change in position in the x direction. 20 meters.
No. Are we looking for how far it's going to land?
Not a distance, not a linear distance, not from here to here, but how far in the x direction does it need to go?
Does it need to go?
Yeah, so the x direction, when you're breaking things up into components, the x direction is completely left and right. So we don't care about how far up or down it is. All that we care is that it makes it from this position over to this position, regardless of where it is. The y position will determine how high we need it to be at any point.
But that'll affect the time in the air and stuff like that.
Right. So we're going to use the y to find the time, and then plug it in over here.
We can't use the x to find the time and the y.
Well, we could. They should be the same.
Okay.
There's going to be two times. Okay. So what's going to happen is that this thing is going to be projected. We want it to land at that position.
Yes.
So this is our initial point, and here's our final point. As far as the x goes, that initial point is 20 meters to the right. The final position is 20 meters to the right of where we started. So that is what we put there.
Yes.
We're going to find a time, that time it takes to get from this position over to here. The ball can move over there.
But not make the height difference.
But not make, we don't worry about the height difference.
Okay.
When we get to the y, we're going to find a time at which it's at this height.
Okay.
That time should be the same as the time that it gets over there.
And if it's not, then we'll know.
Then we'll know it didn't.
Enough or it didn't.
Right.
So, okay. So depending on the time, will be too short or too long?
Depending on the time will be for x, because x at the end of x is when we get to 20 meters. So
Oh. Okay.
Right. The time that we find in x is when we are at 20 meters. At 20 meters away. It could be way up here. It could be way down here. It could be hypothetically below the
So we're
ground.
only looking at the 20 meters away. Okay.
Right. For the x direction, we're only caring about the 20 meters away. Okay. So can we solve for time in the x direction? Yes. Using what?
Delta D
Delta D.
equal to BIT plus 1/2 t squared.
Yeah, so in the x direction we use this equation. Almost always use that when you're talking about projectiles. Change in position, 20 meters. Initial velocity, 12.5 meters per second times the time, t, plus 1/2 the acceleration, throw.
So that whole thing's gonna be
Right. T squared. That whole thing goes away. So 20 meters is equal to 12.5 meters per second times T. So T is 1.6 seconds. So at 1.6 seconds, we don't know anything about how high it is. All we know is that 1.6 seconds, it is at this plane, 20 meters away. Regardless of where it is, we know that it's there. So that doesn't tell us did we make it, that doesn't tell us where we are. It only tells us where we are vertically. So 1.6 seconds, we are at 20 meters away. Now let's look at the y direction. Vy, Vi, Vf, acceleration, change in position, time. So we know that the time is going to be the same. Assuming the time is the same, what we're going to be able to figure out is where this thing is after 1.6 seconds. Vertically, it's going to go up, and then it's going to come down. It'll take however long it takes. We want to know specifically where is it vertically at 1.6 seconds.
Okay.
If it's at 10 meters, it's right there. If it's at 20 meters, it's way up here. If it's at negative 20 meters, then it didn't make it at all.
Okay.
So we'll be able to figure out where it is at 1.6 seconds on this vertical plane, or this horizontal plane. So currently, we're there. We're going to use the y direction to figure out where on that line we are.
Changing distances.
No.
Change of D, we don't know delta D.
We don't know delta D. We don't know. That's what we're looking for.
okay.
Where are we along that plane? So I know I didn't say what we're looking for in the problem, but that's what we're looking for. Acceleration.
Negative 9.
Gravity.
Section.
Squared.
Final velocity, negative 21.65.
No. That would only be if we're symmetrical. And this will definitely not be symmetrical. And initial velocity?
21.65.
21.65. Does everybody understand how he got that?
Okay.
So he used this component. So remember, we've got this triangle, 25 and 60, and for the x component, for this value, we solve for that. For the y value, we're going to solve for this side over here. You can use tangent, or probably preferably use sine. Sine of 60 degrees is y over 25. So 25 times the sine of 60 is equal to the y component that we have down here. That evidently is 21.6. We should have done an easier example to start off with. It's okay. Okay, so we're looking for where we are vertically at 1.6 seconds. So what do you want to use? We know VI, we know A, we know T.
I think that uses this here.
What uses those three? The one we just did. Change in D is VIT plus 1/2 the acceleration times squared. Change in D is what we're looking for. Initial velocity, 21.65 meters per second. Time, 1.6 seconds plus 1/2 the acceleration. Time, 1.6 seconds. Squared. Change in D is whatever that math tells us it is. 1.6 squared times 10 times 0.5. 21.65 times 1.6 minus 12.8. 21